Okay, hello everyone. So I'll introduce myself first. My name is Stephen Creagh, and I'm an applied mathematician at the University of Nottingham. I'll say something about myself first and then start talking about our courses and what to expect at university. So my own background is that I'm interested in modeling wave problems. So early in my career, I was looking at quantum mechanical problems, which could be a wave type thing you would like to look at. And more recently, I've been interested in applying those sorts of techniques that we learned about in quantum mechanics to problems like acoustics and wireless communications, which are very similar mathematically, even though the technical background is quite different. In terms of teaching, you would encounter me in first year through, for example, our mentoring scheme. We have something called PASS, peer assisted study support, where students in later years help their first years adapt to university life. And you will encounter that both as a recipient of the PASS scheme in your first year, and later years you can, for example, volunteer to help out first years as well. And I have in the past also taught the first year applied mathematics module, and today's taster lecture is going to be adapted from the sorts of things you would learn, for example, in that module. Now, before I start talking about the taster lecture, I thought it would be interesting just to say a few words about the differences maybe between applied maths at university versus what you're experiencing at school. And to a large extent, if you're at school, probably applied mathematics corresponds to mechanics. And I really like mechanics as a subject. I find it really, really interesting. But I can see that some students from A level, if you're doing lots of problems with blocks on pulleys and bits of string and tension, I know some people find that not very interesting. So what I'd like to make a point is, A, mechanics will get interesting when you come to university, much more so than A level. And secondly, applied mathematics is very, very different. It can involve things which have nothing at all to do with mechanics. But let's give an idea of some of the things that you would encounter at university in applied mathematics. So following on from the sorts of mechanics you learn at A level, you can, for example, carry on learning about mechanics, and I promise you it gets more interesting as you learn at university. You learn more interesting ways of looking at equations of motion and mechanical problems. And for example, still in science, within areas such as molecular dynamics, solving classical equations of motion is still an interesting problem. And there are still mathematical things that people like to work out there in research. As you carry on at university, mechanics leads into really interesting stuff. For example, it leads naturally into the theory of relativity and gravity. And for example, you can do projects and or modules in things like black holes if you stay for a 4-year degree. And that really sounds much more interesting than pulleys on blocks, doesn't it? And of course, it also leads to quantum mechanics, which, even though it's got mechanics in the title, is mathematically very distinct. And again, really, really interesting. We've got active researchers in the school who, for example, look into things like quantum computing and quantum information, as well as, for example, quantum theories of black holes and gravity as well. So mechanics itself becomes really interesting, and it branches out into lots of different topics once you follow on at university. But also, actually, applied mathematics is but much more than that. So one of the things that we're going to be talking about today is within modeling. And for example, we have, again, a large research group who are very active in modeling biological and medical problems using applied mathematics. And for example, topic of the day is epidemics and pandemics is something that's very important for to model mathematically. And we have people who are also interested in other areas as well within biology and using mathematical models for those. And again, we've got modules not in first year, but in later years, for example, in your third year, where you can get practice applying your modeling skills to biologically and medically motivated problems. Maybe a little bit connected to mechanics, you can, for example, study fluids. That could lead on to things like climate modeling and weather forecasting and so on, not necessarily as part of the modules you'd learn at university, but I, for example, have had students who have gone on to do research careers in weather forecasting, for example. And more generally, the area I'm in, which is wave propagation, has lots of applications in areas like mobile communications. You're sending out waves, they hit different buildings, and you have to model the signal strength of your mobile phone. And that actually is very much a modeling and mathematical problem as well. And similarly, acoustics is mathematically very similar. So even though they seem like very different problems, they're both things that you would want to study within applied mathematics. So the subject is really, really broad at university. Today I'm going to focus on one particular area, which is using mathematical models for things like pandemics and epidemics, and show you how it's used in practice, in action. And this is a set of techniques that you would learn about in your first year applied mathematics module, for example. Now, before we get started, as we said, that there are some quizzes coming up, so I'd like to have a practice session first. So you should, in the chat, have some links to a Pingo quiz. So if you go to pingo.coactum.de and you go and click on that link, you should, I hope, now be able to give your response to the quiz. So you can tell me how much you love or hate mechanics. If you maybe are interested in all these other applications, but not so much in mechanics, or if also it sounds wonderful, that would be great for us to know as well. And this will hopefully give you some practice at using this quiz before we carry on. Okay, great. So we've had some responses to that, and I'm really happy to know that at least no one hates mechanics. So that's a really good start. Okay, so let's start exploring the sorts of things you would learn as part of an applied mathematics module. Before we get started, I would like to just establish what I'm expecting you to know from A level and be familiar with. So we're going to be looking at models which involve rates of change in calculus. And I'm going to assume you know that a derivative is a rate of change. Now, you may be more used to in calculus having a y given as in terms of x. In these modeling problems, we're going to be looking at how things evolve in time. So they'll be functions of a variable t instead, representing time. And confusingly, instead of y or x as a function of t, I'm going to use p because it's going to refer later on to populations. For example, the population of infected people if some a disease is spreading through the community. So what you especially need to know is that if you differentiate p as a function of t, and if that derivative is a positive number, it means that p is increasing as t goes forward. And if it's a negative number, then p is a decreasing function of t. Now, it turns out that what I'm going to be concentrating on today is looking at trying to understand how to solve problems without going to long, complicated equations. So we're not going to do lots of detailed calculation, but I will want you to know that the derivative of the exponential function e to the kt is k times e to the kt. One way we can state this is you notice, for example, that it's just k times p. So the exponential function is very important because when we differentiate it, it's its own derivative up to a constant factor, in this case k, and k is going to be used as a constant or a parameter throughout this talk. So I'll assume that you know that. And I will also assume that you're familiar with graphs of exponentials. So if I plot e to the kt, where k is a constant, if k is a positive number, then as t goes forward, it's an increasing function as I go from left to right on the graph. And if k is a negative number, it's a decaying or decreasing function as I go from left to right. And maybe one more thing that's useful to just bear in mind is that if I give you a new value of k that's still positive but bigger, it's increasing but at a faster rate, and the curve is increasing more steeply. So that's essentially the bank of knowledge that I'm going to assume you know going into the next few slides. So what we really like to do is an example. Well, it's impossible nowadays to avoid the fact that we're in a COVID epidemic. So I'm going to use that as motivation for some modeling. And it turns out that these models are essentially like things that you would have learned anyway in this first year applied maths module. In previous years, we would have talked about fish in the sea or rabbits on an island growing in population. For this talk, I'm going to pretend that P represents the number or the population of people infected with some disease such as COVID. And I'm sure we're all more than familiar now with seeing graphs of incidence and deaths, for example, of COVID as it spreads. And I'll just point out that this is something we can hope to model. Now, one thing I'll point out about a lot of these graphs is that very often you'll see that especially at the beginning of pandemics, we get a rise in the incidence of deaths or infections, which looks a lot often like the exponential curves I showed on the previous graph. And it turns out that that's not accidental. So when we're modeling pandemics, very often these exponential functions we had on the previous slide are really good early on. But later, as we react, for example, we do social distancing, we decrease the ability of the virus to spread, we get different sorts of behavior, and the curve can do more complicated things. And of course, it's really important to be able to predict what's going to happen as a result of policy changes or mutations in the virus and so on. And that's going to come into modeling. That's the sort of thing that you would learn as part of applied mathematics at university. So what I'd like to do is build up a nice simple model to explain COVID. Unfortunately, COVID is just a little bit too difficult for the techniques you learn in first year for a very simple reason that I'll say in a moment. So I'm actually going to do a simplified model which doesn't quite work for COVID, but can be adopted for COVID later on. So I'm going to call it a not COVID epidemic, which has lots in common, but one important feature is going to be different. And to develop this model, again, an important part of the modeling process is that we build up models which are at the beginning simple. We learn to understand them, and then we improve them. We try to make them more realistic as we carry on through the modeling process. So at the very beginning, our models are often really, really simple, and maybe sometimes with a slightly crude way of modeling the world around us. Now, one of the important things we're going to do in this model is that we all know people are discrete. You don't have half of an infected person with COVID. Nevertheless, I'm going to model the population of infected people, the number of infected people with the disease, let's say in the UK as a whole, as a continuous function of t, even though we know it's counted discretely. That's often a really useful approximation, and you will see this very often in public representations of COVID incidents. The real data is very jumpy and, for example, oscillates a lot due to reporting at weekends and so on. In broad strokes, when we're modeling, we like to model things in terms of continuous curves, which are often, in any case, more informative than the noisy data underneath them if we're trying to predict what's going to happen in the future. So this function P, capital P, represents the number of infected people in some community. Now, as people are infected, we know that the problem is that each infected person can infect people around them and so on. So the rate at which new people are added to this infected population depends on how many people are already infected. The more infected people there are, the more people will become infected in the coming days and weeks. And that means that the rate of change of P, with respect to t, that derivative function we talked about, is proportional to the existing population. Now I've written a twiddle instead of an equals here because it's not the whole story. There are other things I'll have to include in a moment. So I've written it as the PDT has a contribution which I've written down as b. B is a number times p, the thing that we're trying to model. Now b isn't given normally in terms of 1 or 2, it's a number that you would have to get by communicating, for example, with the Office of National Statistics. It itself, and determining this number b, is a separate problem. As far as you're concerned, it's just a symbol representing a number that we can think of often as being a constant of some sort. Now, people don't just get infected, they also recover. So as people recover, they're removed from this population of infected people. So that gives a negative contribution that decreases the infected population. So again, that will contribute something like minus CP. And if we assume people recover at more or less the same rate, then a certain fraction of them might recover every day. Now, this is a very simplified model. People recovering today will normally have been infected 2 weeks ago. I'm ignoring that lag, and in this very initial simplified model, I'm simply saying a certain fraction of people are going to be recovered every day that the epidemic goes on. So far, that's actually not too far away from COVID. The last simplification I'm going to make, which makes it not COVID, which is that after people are reinfected, they can be reinfected again. So you don't get immunity from this not COVID epidemic. I do that because it'll simplify the model. It means that I don't have to keep track of how many people are immune as well as how many people are infected. It makes the model a little bit simpler. And for example, in terms of what you learn at university, it means that techniques you learn in first year can be used to analyze this, whereas a full COVID epidemic model would need second year techniques to do it because it's got more things to keep track of. But qualitatively, a lot of the techniques are very similar. Okay, so let's start building this simplified model. So we've mentioned already that the rate of increase or rate of change of the infection population P gets a positive contribution from transmission leading to new cases and a negative contribution coming from people who've recovered. So one is plus and the other one is minus. But both of them are proportional to the existing population, so that we can simplify it. We've got a common factor of P, and I can write that as some constant I'll call K times the population P, and K is B minus C. Now I should say I've called K constant, it need not be, so that's something I'll come back to later on. In the simplified initial models, K can be constant, but later on maybe I'll allow K to change as well. So let's start asking ourselves how we start solving this model. Well, first of all, you'll notice that it all depends critically on whether K is positive or negative. If that parameter K is a positive number, it means the population is increasing. The PDT is greater than 0. And that usually corresponds to the beginning of an epidemic, where we saw that rise that looks suspiciously exponential in the published data. If, for example, as we do social distancing and we reduce transmissibility, maybe the transmission part of our equations gets smaller. The parameter B that again we have to decide by talking about the NHS or Office of National Statistics, that can get smaller, and maybe then K could become negative, and that might characterize when we're starting to recover and numbers are falling later on in the epidemic. So this equation can account for both sorts of behavior. So let's try to solve it. So as I said, I'm mostly going to be trying to solve equations today using pictures, but let's use a couple of equations. And to start, I'm going to assume that this number K is a constant. It doesn't change as a function of time, and it doesn't depend on P. In that case, the equation I'm trying to solve expresses the rate of change of P with respect to T in terms of K times P. Now that seems unfair because I want P And I've got the derivative, but it's given not as a function of t, but in terms of something I don't know. So this is an example of what's called a differential equation. We need techniques for solving that, which you would learn in first year as part of calculus and applied mathematics. I'm trying to avoid in this taster lecture having to solve this explicitly. With this simple one, let's just write down what the solution is. And we've seen this before, so we've already seen that the exponential function e to the kt, when I differentiate it, satisfies this differential equation. So that's a good start. We accidentally came across the solution of that in the first couple of slides. And one thing I will point out is that it can actually be changed a little bit. So more generally, I can multiply in front by any arbitrary constant a. You'll notice that if I ask what is the population at the starting time, t equals 0, if I plug t equals 0 into that equation, that constant a, in fact, is equal to that initial population. And again, it then has similar graphs as a function of k, depending on whether k is positive or negative. The only difference to the previous graphs is that now the initial value is a, not 1. That gives me an equation that I can use. And that predicts the exponential growth that we saw at the beginning of the COVID pandemic, for example. Now, let me just ask you a few questions about that. So we're going to work out that we need to modify this equation in a moment. But to do that, I'm going to ask you to answer a few simple questions, maybe not so simple, so have a go with these. And I'll now activate the quiz on Pingo. So you should now be able to access the quiz. And this is essentially asking you what's going wrong with this in the long term. So it's not exponential forever. Is it that exponential functions are growing, whereas we saw in the data that sometimes p decreases as well as increases? Maybe this predicts a number that's too big. If I put t too big into that formula, eventually p will become arbitrarily large. And if t is large enough, maybe we fill the solar system with people infected with COVID, which isn't realistic. It might be that as p gets larger, maybe the fact that k isn't constant is something we need to account for. So as more people are infected, then we need to account for the fact that there are fewer people to infect. And lastly, nobody told me what a is, so maybe that's a problem as well. So I'll leave you finish that, and then I'll answer those questions and carry on. Okay, right, good. Happily, okay, so no one gave D, which is correct, because even though A is the symbol here, we can work that out from measuring the number of infected people at some point before the pandemic fully gets started. So A is something that we can work out what it is, even if I haven't written down a number for it. C is actually the most correct answer. So as a greater population of the, a greater fraction of the population, general population are infected, it gets harder for the virus to find newly uninfected people. If everyone's already infected, it can't find new people to infect. So essentially the assumption that k is constant is unrealistic. We should realistically model it by allowing k to get smaller as p gets bigger. B is also correct, by the way, even though it doesn't explain why the model is going wrong. It gives us an indication that something is clearly not right, because exponential growth can be very rapid. It can't carry on forever, because it would genuinely be true that if you put large enough numbers t into that formula, you will eventually have more infected people than there are atoms in the solar system. So that's clearly not unrealistic forever. And A is not really true, because depending on whether we let k be positive or negative, we can make the solution grow or decrease. But it is the case that we need to let k change in order to get the sorts of features that we've seen. So let's start accounting for that. So in our model, we need to let k, that parameter, or that constant of proportionality, or not constant, be something that gets smaller as p gets bigger. Now, a really obvious way to do that is, for example, to just assume its graph is a straight line. So if I was to plot k as a function of p, it gets smaller. And let's, in this very simplest model, which is something we usually do in modeling, make the simplest possible substitution which will satisfy that criterion. And we're going to assume that the transmission gets smaller as more people in the population are infected. And it could be, for example, and this is something we would like to model, that beyond a certain population size, which I'll call P0, or number of infected people, then the rate of people recovering will be greater than the rate at which new people get the disease, so that in fact k can then become negative, and then the rate of change can become negative and the number of infected people can start decreasing. Now, in terms of getting equations, I can write down the equation of a line, so don't worry too much about this equation. I've written something down which is the equation for a line which intersects the vertical axis at k equals k0 and intersects the horizontal axis at p equals p0. So that's the two numbers I wrote down in my graph. If I was to try to look for explicit solutions to that equation, that would be useful to know, but here I'm going to try to understand the solution using pictures, so the formula isn't so important in this case. What's really important is that k, which occurs in dp/dt, vanishes when p equals p0. And now notice dp/dt is k multiplied by p, so that will also vanish when p equals p0, but it will also vanish then when p equals 0. So now there will be two places where the rate of change dp/dt is equal to 0, one when the population, there are no infected people, and one when p is equal to this number p0. So again, I can write down the corresponding equation for dp/dt. It's a differential equation. And don't worry too much about the right-hand side. It looks complicated. It's something I could solve using equations, but I don't want to, because I want to solve it using pictures and graphs instead. The thing that we're going to notice is that's more important is if I look at the graph of dp/dt as a function of p, whenever that graph is above the horizontal axis, so when dp/dt is a positive number, it means that p is increasing. Remember that from the early slides, and it means that as p increases, it's going from left to right on the plot that I've shown here. If p is above that critical point, p0, then the derivative is negative. That graph falls below the horizontal axis. dp/dt is a negative number, which means that p is decreasing. On that graph, the solution is going from right to left. Right in between, exactly at p0 itself, dp/dt is 0. It's constant, and that's like a steady state, or what we might call an equilibrium. And the equilibrium separates solutions which are increasing from solutions which are decreasing. And all of that information I got just from the shape of the graph. I don't need to know all of these horrible looking equations on the right hand side. Knowing that graph is enough for me to deduce all of that interesting stuff. So in the next couple of slides, to end this taster lecture, I'm going to use that in a worked example. But to get started on that, I'm going to ask you to attempt to do the following explicit example. Now, I know that when I've been doing the slides before, I've had A and B and P0 and K0 and K. Everything looks like lots of different constants, etc. You need That flexibility, if you're doing a real live modeling problem where you need to get values of constants by talking to the NHS or the Office of National Statistics, but for doing simpler problems, let's just write down an easier example where the right-hand side is easier to write down. Let's try to solve the equation dp dt is 2p minus p squared. Now I'm going to start the survey and give you a chance to answer these. Try to solve these as best you can. Don't worry if you can't, because I'm going to go through the solution in a moment as we finish this taster lecture. So with that equation, you have to answer A, does P increase and gradually approach the value P equals 2? Maybe it decreases and approaches the value P equals 0, you decide. It could be that it stays forever at its initial value P equals 1, so it starts off at time 0 at the value 1. If that's an equilibrium, it'll stay there forever. Or it could be a bit like the exponential function where it keeps growing forever, gets arbitrarily large, fills up the solar system eventually, and then we have to adjust our model. So give your best answers on the quiz, and I'll go through that solution in a moment for you. Great, okay, so we've got a number of answers here. Okay, so let's go through them. It turns out that in this case, and I'm going to explain this on the next slide, the answer is actually A. So a bit like in the previous problem, between 0 and 1, dp dt is going to be a positive number. And as p increases, because the dp dt is positive, it'll keep increasing until it reaches a p where dp dt is 0, which is p equals 2. P equals 0 is an equilibrium, but the solution goes away from P equals 0, not towards it. And even though it looks feasible, P equals 1 is not an equilibrium, so that's not correct. And it turns out that because it reaches this limiting value of 2, in this case, the solution doesn't keep going forever. So let's see why that is the case. So let's go through this equation and try to break it down. So I would like to know for which values of P is dp dt positive, and for which is it negative. It always helps in this case to try to work out the equilibria, which is where that right-hand side is equal to 0. And in this case, the right-hand side can be factorized into p times 2 minus p. And that's equal to 0 either when p equals 0 or when p equals 2. So those are two equilibrium. And in fact, if you look at that, it's a quadratic right-hand side. So its graph is a parabola. And again, it looks essentially like the example we had on a previous slide, except I've written explicit numbers instead of p0 and so on. And you'll notice here that the graph is positive when p is between 0 and 2. P equals 2 is an equilibrium, as is p equals 0. And the rate of change becomes negative when p is greater than 2. Now, the initial condition in that worked example told us that initially the infected population starts off with the value p equals 1. So that's right in the middle between the two equilibria, 0 and 2. In that region, in that interval where it starts, the derivative is positive, means that p is increasing. So on that horizontal axis, p is moving from left to right. And as it goes rightwards, the rate of change stays positive, but it gets smaller. And it slows down, but it keeps moving rightwards. And in this case, the solution will gradually approach the equilibrium value p equals 2. So that's what we're going to conclude here, that because the PDT is positive in that interval, the infected population increases and approaches the equilibrium value. It should here be p equals 2, not p equals 0. Now we can represent that nicely using something called a phase line. And here, for example, I'm going to represent that information. If my initial population is between 0 and 2, the derivative is positive, the solution moves from left to right, and I indicate that by arrows. And eventually, any starting condition in that part of the real line ends up on the equilibrium p equals 2. If I have a population on the right of that, the arrows are pointing leftwards because the solution is decreasing. And again, here, my solution on the p-axis goes from right to left, and it decreases and approaches that equilibrium value. So that's a really important lesson, that we didn't have to solve very complicated differential equations. We can just draw graphs and work out qualitatively what the solutions are like. And here's the lesson. So we can, and you will learn techniques to solve these sorts of differential equations at university. Really important, lots of additional important information from them. But this sort of qualitative information we get from pictures and diagrams, looking at things like equilibria, tell us an awful lot about the solution without very complicated equations. And that's something that's really, really powerful in dynamics and modeling and differential equations later on. Looking for things like special structures like equilibria can tell us an awful lot about the solution beyond lots of complicated formulas or even putting things on large computers. And this is the sort of thing, it's one of the topics you would encounter in your first year applied mathematics modules. So I will leave that as that example. Now, having given that taster lecture, Joel is going to take over and tell you something about her undergraduate courses.